Good morning. My name is Shobha from BSC Chemistry Honors, second year. Today I am going to prepare a video for audio video impaired students of organic chemistry from PPM edition. And my topic is alcohols. Objective of this unit are to study the alcohols, their structures, nomenclature, classification on the basis of number of OH group present like monohydric, dihydric and polyhydric alcohols. Classification on the basis of nature of a carbon attached to OH group like primary, secondary, tertiary alcohols. This unit also aims on method of preparation of alcohols with their physical chemical properties, acidic basic character, chemical reaction of alcohol like acid, catalase, dehydration, etc. Study on chemical properties of dihydric, polyhydric alcohol can also be aimed in this unit. Introduction. Alcohols are organic compounds in which one or more hydrogen atom from hydrocarbon can be replaced by hydroxyl group. They are some of the most common and useful compounds in nature, in industry and around the house. The general formula for the simple acyclic alcohol is CnH2n plus 1OH, where N is 1, 2, 3, etc. The saturated carbon chain is often designated by the symbol R so that ROH can represent any alcohol in the homologous series. Alcohols can be viewed as organic analogues of water in which one hydrogen atom is replaced by an alkyl group. The simplest and commonly used alcohol are methanol and ethanol. They occur widely in nature and have many industrial and pharmaceutical applications. Aromatic compounds in which contain a hydroxy group on a side chain behave like alcohol are called aromatic alcohol. In these alcohols, OH group is attached to a sp3 hybridized carbon atom next to an aromatic ring. In some alcohols, the OH group is attached to a sp3 hybridized carbon next to the carbon-carbon double bond, that is an alicyclic carbon known as allylic alcohols. In some alcohols, OH group is bonded to carbon-carbon double bond to a vinylic carbon or to an aryl carbon. These alcohols are also known as vinylic alcohols, acyclic and benzylic alcohols, which may be primary, secondary and tertiary in nature. Classification of alcohols. Alcohols are classified into different following types on the basis of number of OH groups present in molecule and nature of carbon attached with OH group as follow. Monohydric alcohols. These compounds contain only one OH group. Dihydric alcohols, these contain 2 OH group. Trihydric alcohols, these contain 3 OH groups. On the basis of nature of carbon atom attached with OH group, the monohydric alcohols can be further classified as primary, secondary or tertiary depending on the number of carbon atom bond to hydroxyl bearing carbon. Primary alcohols. A primary alcohol has one alkyl group attached to the carbon bond to the OH, a compound in which hydroxyl group is bounded to primary carbon. Primary alcohol have the group CH2OH, where the carbon atom with the alcoholic hydroxyl group has at least two additional hydrogen attached to that carbon. Primary alcohol has OH group bonded to a carbon which is bonded to one another carbon. Secondary alcohol. A secondary alcohol has two alkyl group attached to the carbon bond to the OH. The hydroxyl group is bonded to secondary carbon. Secondary alcohol have group CHOH where the carbon atom with the alcoholic hydroxyl group has one additional H atom attached to it. There are two R. R stands for the other organic carbon group and the alcoholic hydroxyl group is attached to secondary carbon. Secondary alcohol has OH group bonded to a carbon which is bonded to other two carbon. Tertiary alcohol. A tertiary alcohol has three alkyl group attached to the carbon bond. The OH, the hydroxyl group, is bound to a tertiary carbon. Tertiary alcohol have the group COH, where the carbon atom with the alcoholic hydroxyl group has no additional H atom attached to it. If we replace hydrogen with the OH group, we get following group of three alcohols: primary, secondary, and tertiary alcohol. Next, nomenclature of alcohols. According to IUPAC system of nomenclature, alcohol are called alkanols. They are named as the derivative of a corresponding alkane in which the electron of the alkane is replaced by OL. The IUPAC have come up with a set of rules that are used to name any alcohol regardless its complexity. These rules are summarized as: name the longest continuous chain to which hydroxyl group is attached, count the number of carbon atom and identified corresponding alkane. Second, number the longest chain to give the lowest possible number to the carbon bearing hydroxyl group. Locate the position of hydroxyl group by the number of carbon to which it is attached. Combine the name and location of other group, the hydroxyl group location and the longest chain into final name. If there are more than one OH group, do not remove electron from the suffix but add a di or tri prefix to OL suffix. Identify and locate other branches on the chain so that they are named alphabetically and their carbon is hyphen into the front of name. For example, CH3OH common name is methyl alcohol and IUPAC name is methanol. Similarly, CH3 CH2OH common name ethyl alcohol and ethanol. Next is preparation of alcohols. The following method used for the preparation of alcohols: hydrolysis of alkanes. Haloalkanes can be converted to corresponding alcohols using aqueous NaOH, KOH, or CaOH twice. With this method, primary and secondary alcohols are formed from a primary secondary haloalkanes. This is a type of nucleophilic substitution reaction. This reaction is useful only with the reactants that do not undergo E2 elimination readily. Reduction of carbonyl compounds. Carbonyl compounds which contain CO groups such as aldehydes, ketones, carboxylic acid, esters can be reduced to alcohols. Aldehyde give primary alcohols while ketone yield secondary alcohols either by catalytic hydrogenation or use of chemical reducing agent like lithium aluminum hydride. Carboxylic acid and esters also give primary alcohols on reduction with hydride reagent such as lithium aluminum hydride and sodium borohydride. Third is from hydration of alkenes. Hydration, addition of H positive or OH negative across a carbon-carbon double bond to give alcohols. It is an electrophilic addition to H2O2 alkene. Alcohols can be prepared by adding water to an alkane in the presence of strong acids such as H2SO4. Because these reactions follow Markovnikov rule, the product of reaction is often a highly substituted secondary and tertiary. Fourth is oxidation of organoboranes. When an alkene reacts with BH3, a boron hydride, in THF solution, organoborane is obtained. Hydroboration followed by oxidation will produce an alcohol. Since BH3 has 3 hydrogens, above addition can occur 3 times to give trialkyl borane. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. The overall reaction is addition of water across double bond opposite to that of Markovnikov rule, and the reaction is reduced selective, producing the least substituted alcohol. Expect ethyl alcohol. No other primary alcohol can be obtained by this method. However, hydroboration of terminal alkenes gave primary alcohol. Fifth, from Grignard reagent. Alcohol can be easily be prepared by using Grignard reagent as follows by reaction of aldehyde and ketones. The reaction of Grignard reagent with formaldehyde produce a primary alcohol with other aldehyde secondary alcohols and with ketone tertiary alcohol. In this method, alcohol is prepared with the formation of new carbon-carbon bond. जैसे आर एम जी एक्स सी R C double bond O R dash in the presence of THF gives alcohols. All other aldehyde yield secondary alcohol in the on reaction with Grignard reagent. With ketones, Grignard reagent give tertiary alcohol. By reaction with esters, produce tertiary alcohol in which two of the substituent on hydroxyl bearing carbon are derived from the Grignard reagent. By reaction with epoxides, Grignard reagent react with epoxide to yield primary alcohol containing two or more carbon atoms. Fifth is by fermentation. Ethanol is prepared on large scale by using fermentation process. It involves breaking down large molecule into simpler ones using enzymes. Yeast is added as a source of enzyme. Yeast convert the reactant glucose or fructose into ethanol and carbon dioxide in presence of zymase enzyme. Next is acidic nature of alcohols. Alcohols can act as Bronsted acid as well as Lewis base due to the donation of the proton or presence of unpaired electron on oxygen respectively. Alcohol are very weak acids because the alkyl group pushes electron towards OH so that the oxygen does not strongly attach the electron in OH bond. Furthermore, once Ro negative ion is formed, it cannot be stabilized by the delocalization of charge. Thus, alcohols react only a very slight extent with alkali but will react with the very electropositive metals undergo anhydrous conditions to give alkoxide with the general formula Ro negative and M positive. Reaction of ethanol with sodium CH3 CH2OH 2 mole plus 2 mole of Na gives 2 CH3 CH2O negative Na positive plus H2. Addition of water will regenerate alcohol readily. The reaction is much slower than the reaction of water with sodium. Alcohol tend to be slightly less acidic compared to water. The higher value of pKa value, the lower is the acid strength. The reaction of alcohol with sodium can be used to deposit excess sodium in laboratory. Even alcohol are neutral to litmus and do not react with alkali like NaOH but contain active hydrogen atom so react with Na or K metal. When ethanol is react with sodium hydroxide, there is no reaction. Reactivity of alcohol towards metal, primary, secondary, and tertiary alcohol, and electron releasing group increases electron density on oxygen, tend to decrease polarity of OH bond. For example, with methanol. Lower alcohols are colorless liquids with a characteristic smell and a burning taste. The higher numbers, more than 12 carbons, are colorless wax like solid. Because of hydrogen bonding, alcohol tend to have higher boiling points than comparable hydrocarbons and neither of similar molecular weight. Alcohol exists associated molecules due to the association of molecule in the liquid phase through strong intermolecular H bond between hydrogen atom of one molecule and oxygen atom of another molecule. Oxygen hydrogen bond is polar because oxygen is much electronegative than hydrogen. The lower members have low boiling point with the increasing molecular weight boiling point kept on increasing gradually. For example, boiling point of methyl alcohol is 118 degrees Celsius where the boiling point of isomeric diethyl ether is 36 degrees Celsius. Stable solubility. The general rule in solubility, like dissolve like the hydroxyl group, generally it makes alcohol molecular polar and therefore more likely to be soluble in water. Hydrogen bonding also have an effect on water solubility. The OH group of alcohol can hydrogen bond with water, so its portion of alcohol is hydrophilic. On the other hand, alkyl chain in alcohol is similar to hydrophobic molecules with hydrocarbon do not mix with water. Compounds like alcohols that have electrophilic or electrophobic regions are called amphiphilic. The water solubility of given alcohol depends on whether the hydrophilic OH or hydrophobic alkyl chain dominates. Alcohols with a shorter carbon chain are usually more soluble in those of with longer carbon chains because increasing size of non-polar chain disrupt the hydrogen bonding network. Formation of hydrogen bond in water will increase solubility. That is why alcohols are much more soluble in water than their corresponding alcohol. Aromatic hydrocarbons, alkyl halides, aryl halides, amongst isomeric alcohols, the solubility increases with branching. The boiling and melting point will also increase with carbon chain length. Longer the alcohol's carbon chain, better the chance that alcohol will be a solid at room temperature. Alcohols show higher boiling point than alkane and ethers of a similar mass due to hydrogen bonding. Since there is no any possibility of hydrogen bonding in ether, the force between the ether molecule is much weaker than can be much more easily vaporized. Comparison of boiling points of among isomeric alcohols. 1 butanol boiling point is 118 degrees Celsius. 1 2 methyl 1 propanol is 108 degrees Celsius. 2 methyl propanol is 83 degrees Celsius. The viscosity of small alcohols is much higher than the viscosity of alkanes. Generally, alcohols are higher than water, less dense than water. Density of alcohols increases with molecular mass. Chemical reactions of alcohols. Alcohols act as both nucleophile as well as electrophile. The bond between oxygen and hydrogen is broken when alcohol react as nucleophile, and the bond between carbon and oxygen is broken when they act as electrophile. The chemical properties of an given aliphatic alcohol depend on the nature of alkyl group and the properties of hydroxyl group. Based on the cleavage of oxygen and hydroxyl group, reaction of alcohol may be divided into two groups. Reaction involving cleavage of OH bond. Acylation of alcohol. When alcohol react with acyl halide and hydride, substitution of hydrogen atom by acyl group is known as acylation of alcohol. Reaction involving fission of ROH bond. The reaction involving ROH bond with the cleavage of carbon oxygen bond are as follow: dehydration, intermolecular hydration forming alkene. Alcohols undergo dehydration to form unsaturated hydrocarbon on treating with a protic acid. For example, concentration H2SO4 or H3PO4 or catalyst as anhydrous ZnCl2 and Al2O3. In this reaction, the OH and the H group removes from the adjacent carbon. Since water is removed from alcohol, this reaction is known as a dehydration reaction or an elimination reaction. Secondary and tertiary alcohol are hydrated under much mild condition. The reaction for dehydrating alcohols depend closely on the structure of individual alcohol. For primary alcohol, conditions required are concentrated sulfuric acid and temperature of 170 degrees Celsius. In seminal ring, always ring expansion take place due to molecular strain and they tend to convert to high stability with large ring. Secondary alcohol dehydrate under milder conditions than primary alcohols. Tertiary alcohol dehydrate under even milder conditions. The main function of the acid to transform to a poor living group OH into very good living group OH2. The order of relative ease of hydration of alcohol is tertiary, secondary, and primary. Tertiary carbocations are more stable and therefore are easier to form. Secondary and primary carbocations, tertiary alcohol is easiest to dehydrate. The order of stability of the carbocation is. Dehydration of secondary and tertiary alcohols containing more than 3 carbon atoms will give a mixture of alkenes. The major product can be determined from Sergev rule. Sergev rule: when an alkene is produced in an elimination reaction, the major product is the one which more highly substituted double bond. The major product that contains the higher number of alkyl group attached to carbon-carbon double bond. Rearrangement of alkyl group of alcohol is very common in dehydration, particularly in the presence of strong acids which are conductive to carbocation formation. Typical examples showing both methyl and hydrogen migration follow mechanism. Intermolecular dehydration forming ether: when an dehydration is carried out at a temperature of 140 degrees Celsius with an excess of alcohol, ether will be formed. This reaction removes the molecule of water from two alcohol molecule casing the 2R group to become attached to an oxygen atom, forming an ether functional group. Halogenation: alcohol can be converted to alkyl halide using one of three reaction with the hydrogen halide. Respective alkyl halide are formed by reacting with the appropriate hydrogen halide, HCl for chlorination, HBr for bromination, and HI for iodination. The reaction involves the initial protonation of hydroxyl group of alcohol. This improves the leaving group stability of hydroxyl group. Mechanism: protonation of alcohols. The alcohol acts as a weak base and accepts the proton donated by the halogen halide. Removal of water molecule and formation of halide through SN2 mechanism, SN1 reaction. For primary and secondary alcohol, it is SN2 reaction. For tertiary alcohol, it is SN1 reaction. Rate of reaction for primary, secondary, and tertiary alcohols. Order of rates of reaction are tertiary, secondary, and primary. The rate can be shown by turbidity in the aqueous layer since the chloroalkane formed is immiscible with water. Reaction with thionyl chloride. Alcohols will react with thionyl chloride to produce alkyl halide. The reaction involves the nucleophilic attack of alcohol on a SOCl2 molecule displacing one of the chloride. Then the chloride will act as the nucleophile in the second step, displace the oxygen from the carbonyl carbon. Reaction with phosphorus halide. Alcohols will react with phosphorus tribromide and phosphorus pentabromide to form alkyl bromides. The mechanism is very similar to thionyl chloride reaction. The alcohol acts as the nucleophile and displays a halide ion from the PX3 and PX5. Esterification. Alcohol react with carboxylic acid, acid chlorides, and acid anhydrides to form esters. The reaction with carboxylic acid, acid anhydride is reversible, therefore water is removed. Soon as it is formed, esterification takes place much faster in the presence of catalysts such as concentration H2SO4. Alcohol can also be react with acid chlorides, acid anhydrides to form esters. The introduction of acetyl group in alcohols and phenols is known as acetylation. Oxidation. Alcohols can be oxidized by various oxidizing agents to aldehyde ketones or carboxylic acids. Oxidation is gain of oxygen and loss of hydrogen. Primary alcohol oxidizes readily, first to an aldehyde, then a carboxylic acid. These two oxidation steps make secure sense because the primary alcohol functional group has two carbon hydrogen bond that can be broken. Primary and secondary alcohol can be oxidized to produce compounds containing carbonyl group, carbon oxygen double bond. Strong oxidizing agents such as hot alkaline As in H2SO4 will oxidize primary alcohol right past the aldehyde to salt of carboxylic acid, in which the acid may be precipitated by acidification. The alcohol, aldehyde and acid retain the same number of carbon atom. Tertiary alcohol has no carbon hydrogen bond that can be broken, so it is not oxidized. No matter how strong oxidizing agent become, it would involve the breakage of the high energy carbon-carbon bonded alcohol molecule. In acidic solutions, tertiary alcohol can be oxidized to give a mixture of ketone and acid, both with fewer carbon atoms than in alcohol. Characterization of oxidation products of alcohol. It means of distinguishing between primary, secondary, and tertiary alcohols. Dihydric alcohols. The compounds contain two hydroxyl group in a molecule. These are dihydroxy components of alkanes. Their general formula is CnH2n plus 2O2. The simplest and most important dihydric alcohol are ethylene glycol. These are classified as alpha, beta, and gamma glycols according to the respective position of two hydroxyl group. Alpha is 1,2 glycol, beta is 1,3 glycol. Nomenclature. For naming polyhydric alcohols, the name of alkane is retained and ending "e" is not dropped with add a di and tri prefix "ol." Such dihydric alcohols are named alkane diols and trihydric alcohols named as alkene triols. Method of preparation. Dihydric alcohols can be prepared by following different methods from ethylene through IC dilute alkaline solution of Bayer's reagent. With O2 in presence of Ag with HOCl followed by hydrolysis from 1 to dibromoethane. Physical properties of dihydric alcohol is dihydric alcohol via glycerol exhibit following physical properties. It is colorless, slippery liquid and sweet in taste. Its boiling point is 197 degrees Celsius. Melting point is 11.5 degrees Celsius. It is miscible in water, ethanol in all proportions but is insoluble in ether. It is toxic as methanol when taken orally. It is widely used as solvent and as antifreeze agent. Chemical reaction of methanol glycols are glycerol molecule is made up of two primary alcohol group joined together. Its chemical reaction therefore those of primary alcohol twice over. Action of sodium. It reacts with sodium at 50 degrees Celsius form to form mono and dialkoxide at elevated temperature. Reaction with HC ethylene dichloride is formed in two successive steps at elevated temperature. Action of phosphorus halide ethylene dihalides are formed as follows. Pi3 produce ethylene diode with H which is unstable and split into I2 and ethylene. Reaction with carboxylic acid give diester depending upon amount of glycol and acid taken. With dibasic acid is formed polymer. Reaction with aldehyde and ketone glycol react with aldehyde and ketone in presence of p-toluene sulfonic acid to give cyclic acetyls and ketols which further may give ketone aldehyde while treating with HiO4. This reaction thus can be helpful to protect carbonyl group. Oxidation of ethylene glycol with HNO3 to yield a number of substances as follows. Glycol gives glucolic aldehyde and this gives glycolics and glycolic acid and then give glycooxalic acid and oxalic acid. Oxidation with KMnO4 and K2Cr2O7 to form formic acid. Oxidation with PbOCOCS3 square in bracket 4 and HiO4 glycol give form aldehyde. Dehydration. Heating with ZnCl2 glycol gives acetaldehyde. When treated with when heated alone at 500 degrees Celsius gives ethylene oxide. Dioxane is obtained when glycol is heated with concentrated H2SO4. Uses of ethylene glycol. It is used as antifreeze substance which prevents the freezing of water in car radiators in cold countries. Due to its high viscosity, it is used in hydraulic brake, printing ink, ball, pen ink, and organic solvents. Used as manufacture of dacron and dioxane as a solvent and as a preservatives, as a cooling agent in airplanes, as an explosive in the form of dinitrate. Large amount of ethylene glycol can be converted to polymers trihydric alcohols. It is triol. The introduction of a third OH group in diol molecule raises the boiling point up to 100 degrees Celsius, increase viscosity and make the alcohol more sweet glycerol. It is designated as Prop 123 triol IUPAC nomenclature. It can be considered as a derivative of propane obtained by replacement of three hydrogen atom from different carbon atom by 3 hydroxyl group. In industry, it is known as glycerine. It occurs as glycosides in almost all animal and vegetable oils and fats. Method of preparation. Glycerol can be synthesized by different methods from fat and oils. On hydrolysis of fat, oil, glycerol, higher fatty acid are formed. By fermentation of sugars, alcoholic fermentation of sugar in the presence of sodium sulfide give good yield of glycerol. Synthesis from propene. Today, much of glycerol is obtained from propene. Physical properties. Glycerol is colorless, odorless, viscous, and hygroscopic liquid, sweet in taste, non-toxic in nature. It is soluble in water, alcohol, but insoluble in ether. It has high boiling point, 290 degrees Celsius, high viscosity. High boiling point of glycerol are due to association through hydrogen bonding purified in lab by reduced pressure distillation and vacuum distillation. Chemical reactions. Glycerol molecule contains two primary OH group and one secondary OH group. Thus, it shows characteristics of both primary and secondary alcohols. Reaction with sodium. Only primary alcoholic groups are attached one by one and secondary alcoholic group is not attacked. Sodium forms monosodium glycerate at room temperature and disodium glycerate at high temperature. Reaction with PCl5, all three OH group are replaced by Cl atoms. Reaction with HCl and HBr. When HCl is passed into glycerol at 110 degrees Celsius, both alpha and beta glycerol monochlorohydrines are formed. If HCl is gas is passed for sufficient time, glycerol alpha dash dichlorohydrin and glycerol alpha beta dichlorohydrin are formed. Reaction with HI. Glycerol react with HI in two ways. When glycerol is warmed with a small amount of hydrogen iodide, allyl iodide is formed. First, triiodide is formed, but due to large size of iodine atom, IO2 comes out from product. When glycerol is heated with large amount of HI, the allyl iodide first formed is reduced to propane, which is presence of excess of HI forms isopropyl iodide. Reactions of HNO3. When one part of glycerol is in thin stream is added to 3 times concentrated HNO3 and 5 parts of concentrated sulfuric acid, nitroglycerin is formed. Glyceryl trinitrate is yellow oily liquid poisonous and causes headache. It explodes violently when heated and rapidly are subjected to sudden shock. It becomes a safer explosive when absorbed on Kelly's in the form of is known as dynamite. Dynamite was discovered by Alfred Nobel in 1867. Reaction with acetic acid, acid anhydride and acid chloride, monodi and triesters are formed. Reaction with oxalic acid, different products are formed under different conditions. At 100 degrees Celsius, with excess of oxalic acid, formic acid is formed. At 260 degrees Celsius, allyl alcohol is formed. Dehydration. Glycerol, when heated alone with dehydrating agents such as potassium hydrogen sulfide and phosphorus pentaoxide or concentrated sulfuric acid acrylaldehyde is formed, which has a characteristic bad smell. This reaction can be used as a test of glycerol. Oxidation. Glycerol give different oxidation products depending on the nature of oxidizing agent. The following products may be obtained during oxidation of glycerol. Dilute HNO3 give mainly glyceric acid. Concentrated HNO3 oxidize glycerol into glyceric acid and tartanic acid. Bismuth nitrate gives mainly mesoxalic acid. Uses. Glycerol is used as sweetening agent in confectionery beverages. Medicines being non-toxic in nature, it is used as antifreeze in automobile radiators in the preparation of good quality of soap, head lotions, shaving creams, toothpaste, and cosmetics, as a lubricant in watches and preservative.